Hello, my name is Nitin. Spiak has sent me a pre-release version 4 of CSAR 3D to evaluate. Version 4.0 marks a new milestone in vector-based array system measurements, as it is for the first time that the limitations caused by a fixed sensor array are largely eliminated for the flat phantom. Version 4.0 has two major advantages for the CSAR 3D users. Firstly, an extended frequency range up to 10 GHz. Secondly, reduced measurement uncertainties to below 30% for any SAR distribution. So, even for devices positioned in touch with the flat phantom shell. Version 4.0 also measures the absorbed or epithelial power density as defined in the new ICNIRP guidelines and IEEE C95.1 standard at frequencies above 6 GHz. Today, I will perform two tests, a verification measurement with the 9 GHz dipole and a full 62209-3 validation using the new Extend Combiner feature. I will also compare the validation results to the ones which are obtained when performing the validation without the Extend Combiner feature. The principle of increasing the spatial resolution is simple. You take multiple measurements shifted with respect to the fixed array. This is similar to CSAR 3D quad, in which the CSAR 3D is moved below the quad top. However, the new solution is simple and does not need any additional expensive hardware. The transmitter, such as the phone or dipole, is randomly shifted within the measurement area, and a smart algorithm determines the random shifts and composes a measurement of much higher spatial resolution. I am now going to demonstrate this with this 9 GHz dipole. The SAR distribution of this dipole is very narrow. The 3 dB radius from the peak is only 4.4 millimeters, which is actually far too narrow for obtaining accurate results for the CSAR 3D array spacing of 7.5 millimeters. The signal generator, amplifier, coupler, and the forward power sensors in the transmitter setup deliver a forward power of 10 dBm to the dipole. Once the measurements are finished, I press the field combiner icon and the system combines all measurements and displays them on the SAR value window. In this case, they are 2.26 watt per kg 1 gram and 0.39 watt per kg 10 gram. The target SAR values for 10 dBm are 2.43 watt per kg 1 gram and zero point 0.4 watt per kg 10 gram. The deviation is minus 7% 1 gram and minus 2.5% 10 gram, and well within the computed uncertainty of 29.7%. For me, this is almost too good to be true. The values for epithelial power density are also calculated and are shown here. They are 22.6 watt per meter square for 1 centimeter square averaging and 9.75 watt per meter square for 4 centimeter square averaging area. Therefore, I extended the test to the entire set of validation sources as defined in Annexure D of IEC 62209-3. I would expect improved accuracy for the VPFA sources and for the frequencies above 5 GHz with the new X10 combiner feature, but hardly any improvements for the other sources as CSAR 3D is already exceptionally accurate for sources with a wide distribution, thanks to the very good isotropy and calibration of the system. I have summarized the results for the 10-gram average SAR values on this plot to compare the single measurement with those using the X10 combiner. The blue bars and symbols show the spread in dB for the deviation from the target values for the single measurements when following the 622093 protocol. The spread corresponds well with the results of the validation by SPIAG for each unit and also to those reported by other laboratories. The yellow bars and symbols show the spread in dB when using the X10 combiner. All deviations are now smaller and most importantly within the plus minus 1 dB and the error lines. Remarkably, this is also true for the frequencies above 6 GHz. This means that CSAR 3D 4.0 meets the plus minus 30% requirements for any SAR distribution. However, we plan to extend this study to commercial phones for final proof and will report back soon. The use of CSAR 3D v4.0 leads to a massive improvement in terms of the accuracy for very localized SAR. It is not as accurate as DAISY systems, but might now satisfy the plus minus 30% limit. We also noticed that the measurement is noticeably faster. I am happy to report that one measurement with a complete evaluation does not take longer than 2 seconds. Thanks for watching this video.